this Schmidt of orthogonalization is kind of long word, but it's just try to make a construct of a normal basis. You want this one. No, forget about all this. Okay. So the idea is that you have a bunch of functions at first. They may not be orthogonal, may not be satisfying this. So you this is kind of this is original is chi 0, chi 1, chi 2 altogether. Then it may be a finite number or infinite number, but doesn't matter. And the idea they are not linearly dependent. So it's like all these chi cannot be expressed as linear combination of other chi. Right? Otherwise, somewhere along the line you get zero out of that. Right? So if you have a set of linear independent function, then you can construct orthonormal basis using this function. Okay, and that it's not a very efficient way of constructing basis, but it's a systematic way to do that. Okay, and the idea is the 0, 1 is trivial because you can define phi 0 as just chi 0 divided by the scalar product of chi 0 itself. Because square root power, right? Because now you can check that this is orthogonal or the scalar product of phi 0. The phi 0. It's just quite straightforward. It's just, because each one has normalization. The numerator is just chi 0, chi 0. The denominator is the square of that, so it's chi 0. 1. Okay, so that's trivial. Right. Now you define the next one in 2 steps. First, you found say a function that is orthogonal to phi 0 using a combination of chi 1 and chi 0, right? And the idea is that if it is orthogonal, you define as psi, what we call psi 1. That is chi 1, right? Projection of chi 1 on the phi 0. The projection is just, so you want the projection. You want to basically expand chi 1 in the basis of phi 0. Just using our rule of doing that is the scalar product of phi 1 with phi 0 along phi 0. Right? So this is like a projection, the scalar product of chi 1 with phi 0, and then multiplied by phi 0, right? That will make sure that chi 1 and phi 0 are orthogonal, right? And you can check that. So you can check that phi 0, chi psi 1, right? Just substitute this into here. So you have phi 0, phi 1, phi 1 minus phi 0, phi 0. We're going to check that scalar product. Okay, so substitute this into here. You got this one. That is just phi 0, phi 1, the first term, minus, this is just a number. Phi 0, phi 1, and scalar product phi 0 with phi 0, which by construction this is just 1, right? So this is C. Is that okay? So you make sure that after subtract the projection of chi1 on phi 0, then this psi 1 is orthogonal to phi 0, but this is not normalized. So define phi 1 as just the same way. Psi 1 divided by psi 1, psi 1. Right? And that makes sure that phi 1 is 1. Right? Just the same way. We just did that. Right? That is your first basis, and define like that. This is just psi 1 divided by number, so that doesn't change the fact that they are orthogonal. So this also means phi 1 C. Right. Is that okay? So then once you know this, you can keep going, right? And like you can go to the next order is again you do it in 2 steps, because now you have phi 0 and phi 1 already. You have phi 0 and phi 1, you want to define this too. So you want to define the intermediate function psi 2, phi 2, subtract the projection of chi 2 on phi 0 and phi 1. So again, subtract this phi 0, phi 2, phi 0, also subtract phi 1, chi 2, right? Just the same way you can check that now chi 2 will be orthogonal to phi 0 and phi 1, right? You can check that like phi 0 psi 2 is this into here, so you have 3 terms. So phi 0 phi 2 minus phi 0 phi 2, and this the scalar product this and that is just 1, and then the last term is the scalar product. This coefficient is scalar product of phi 0 and phi 1, which is 0, right? So you only have 2 terms, and that is also 0, right? And then you can similarly check that phi 1 phi 0. Again, you have 1 phi 2, and this and that the scalar product is 0, phi 1 and phi 0, just like that. And then phi 1 are normalized. And so this is minus phi 1 2. Okay, and so this is trivial fact, but you just double check that you define it correctly. So after you subtract all the projection from chi 2, this phi 2s are orthogonal to both phi 0 and phi 1. And so then you just define the next basis phi 2 by normalize this chi 2, psi 2, right? Psi 2. Okay, and now you get the process, right? So you can keep going and get all the phi, keep defining that. And this is a systematic way to do that, but obviously you see that it's not very efficient. Each order you go, each more basis you try to define, you need to subtract more and more terms. But it's just a lot of work to do that. But it's a systematic way that you can construct all these orthogonal bases. And the choice of this kind are arbitrary as long as they are independent. And one trivial independent basis, I mean, independent function is just power xa. if all these are functional x, then you can define this as just x0, which is just 1, and then x to the 1 is just 8, and x and that will make sure that they are linearly independent. And you can use infinitely many of them, and then just define your a set of a normal basis this way. And then you can get different bases for different definition of your scalar product. So all this definition, all this calculation, we didn't specify the scalar product. We just write it up in abstract form, the scalar product. So it depends on your scalar product that change with. Remember the scalar product we defined. G is some integrate from A and B from the conjugate G and W. So the weight function. So you can define different weight this different scalar product by choosing different weight W or changing different limit A and B. And use this start with the same chi. The set of chi is this just power of x. But then you just change W or change A and B, you can define different set of orthonormal basis function, and that you can generate quite a number of them. I think the textbook has a table. In table 5.1, we have all these functions. The general polynomial, which will go through next semester, and all that different kind of polynomial or different function. Right, just by different scalar product, define using different definition of scalar product, changing the limit, changing W, and you can get a bunch of different basis functions. So that's make it powerful. You can actually use the process to get all this set of functions, right? And although it's very tedious to keep doing that, yes.